So let's talk about an introduction to gas chromatography. So the first thing I'll tell you is that all of the fundamentals, that's, things like resolution, Van Deemter, sources of band broadening, um, calculating resolution, everything really that we talked about as kind of foundational information on chromatography before we got to instrumentation of HPLC, it all still applies. Um, so there are some very specific differences between GC and LC. And so I thought a good introduction to GC would be to highlight essentially two of these, right? And I want to just, in a few minutes here, um, look at two major differences. And this is before we'll get to the instrumentation or anything, just two major kind of conceptual differences. And we're going to split these into two. We're going to say, we're going to look at one big downside to doing this, which we've mentioned in the past, so it'll be familiar. And we're going to look at one major benefit to doing GC. So let's start with the downside. So GC only applies to volatile compounds. So how does something become volatile? The first thing is it has a low molecular weight. And we're going to put sort of a rough rule of thumb cap on this. The GC is really only looking at molecular weights that are less than about 400 AMU. Okay, so anything bigger than about 400, you can forget about GC because it's not going to be volatile enough. But it's not everything that's this small because quite a few things that are this small don't fit the second category, which is they need to be thermally stable. Right, and it's not uncommon to see temperatures up to 200 to 300 degrees C involved here. So we're talking about really thermally stable. You need to be able to heat your molecule up to these kinds of temperatures before it falls apart. And so this really is only something like 15% of known compounds. Okay, so GC is not the solution for everything. It certainly is not anything like the kind of broadly applicable tool that LC is. So it begs the question, why do we do this at all? Well, the answer is there's a major benefit, uh, and it is directly related to the instrumentation, which is fun for me because that's what I like to teach. So let's talk about that. So here's the big benefit of GC. So modern GC, this was not always true. GC was invented with packed columns the same way LC was, but modern GC uses open tubular columns. So whereas for LC, right, we have this packing, and the stationary phase lives on the surface of each of these particles. In GC, we have a slightly different column geometry. So we have a tube still that we're flowing down, but instead of being packed with stationary phase media, the walls are coated in it. Right, so those dashed lines represent where the stationary phase is. So let's do that. Stationary phase is here. And that means there is this nice open path down the middle of the column. So let's talk about why this is a good thing, right? So why is this good? And it comes down to Van Deemter. So here's our flow velocity. Here's our height equivalent to theoretical plate. We want to be as low as possible here. Lower is better, right? And we've talked about three contributors here. We have, that's the B term. That's the C term. So this is longitudinal diffusion. It says the longer you're in the column, the more diffusion you get, the broader your peaks get, the poorer your height. The poorer your height gets. So the longer you're in the column, that means the slower you go, the worse you get, right? C is the resistance to mass transfer. This says that basically your analytes need a certain amount of time to be able to do their extracting into and out of the stationary phase. And so the faster you go, the less time they get to do that because they zoom right past the stationary phase particle. And so that's bad. So these two are in competition with each other. But the third factor we talked about, the A term, right? That's our eddy diffusion. It's also called the multi-path term. The A term refers to the extra band broadening you get because, and when you're going through a packed column, one molecule of identical composition could take a much straighter path through here than another one that ends up winding just by random diffusion around many particles. Okay, so the beauty is that open tubular columns, right? Well, we'll just abbreviate this OT columns. Open tubular columns, they have no A term. There is no multipath that these analytes can follow. They're all following exactly the same path straight down the middle. So that's great. It's going to give smaller heights equivalent to a theoretical plate, which gives larger numbers of theoretical plates, which ultimately leads to better resolution because your peaks are all much narrower, and so you're solid there. You get two peaks that can be closer together while still maintaining their separation in space. Okay, that's why open tubular columns are good, and we use them in GC. So if that's the truth, if we're saying, here's a huge benefit, we gotta answer the other side of the coin, right? Which is, if this works so well, why don't we do it for liquid chromatography, right? If it has all these benefits, why don't we just do it for all chromatography? So let's answer that. Why not open tubular columns in LC? So let's remind ourselves of when we talked about UHPLC. The concept here was smaller particles and those smaller particles gave a reduced C term. This worked because the smaller the particles, basically the more surface area there was, the more tightly packed they were, and the smaller distance any molecule needed to diffuse before it saw some stationary phase. That turned out to be really good for getting high quality resolutions, reducing the C term of our Van Deemter. It costs in a lot of back pressure. You need a really good fancy pump to be able to push through these really tiny particles packed in there, but you get something for it. Think about this though. If smaller particles reduces our C term, actually open tubular columns are sort of the exact opposite of this. We are purposely making a much larger distance for the analyte to have to travel to be able to see the stationary phase, right? So if two particles packed really close together gives us better C term than two walls of stationary phase as far apart away from each other as the diameter of the tubing is going to really kill us on the C term, right? So open tubular columns are the exact opposite of this. And in LC, if we were to use, and people have, by the way, there's literature on open tubular LC all over the place. But if you use open tubular to reduce your A term, you end up paying a big, big cost in terms of your C term in the Van Deemter equation. And so the key difference between, well, the key difference in this context between LC and GC is the diffusion coefficient, or the diffusion rate, of the analyte. Let's look at a picture of how that would look, right? We're going to draw two open tubular columns. We're going to say that this is open tubular LC. Right, here's some stationary phase on the wall. This is open tubular GC. Make this just a little bit longer for illustrating my point. Right, there's stationary phase on the wall. And we're going to take an analyte, and we're just going to flow down the middle of each of these things, right? Remember, the thing that gets the analyte, so here's our analyte molecule. The thing that gets us, I'm going to use a smaller marker here. I hope this is going to show up on the camera. Okay, the thing that gets us here from the middle to the stationary phase is just diffusion, right? It's just random motion of this thing. In LC, let's just make sure we're labeling these LC, GC. In LC, that diffusion is much slower, but the linear flow rate is going to be roughly the same, or it's going to be relatively high compared to the diffusion. And so this thing's just kind of diffusing along as it goes through, and boom, there we go. It has diffused into the stationary phase. It spends some time there, and then it comes back out, and it diffuses again. And it just keeps diffusing until, oh, there we go. It's now extracted again into the stationary phase, and at some point later it's going to come out, and there we go. So in the context of our picture here, we saw move back to a darker marker here, a larger marker, two stationary phase interactions. Okay, a gas molecule flowing down this thing, it diffuses much more quickly. That's just the nature of gases, right? They have higher diffusion rates. And so it's going to go down here, it's going to pop out, it's going to come out here, maybe it'll come back there, back up here again, back in here, back in here. So it's seeing a lot more opportunities here. Let's count these up. 1, 2, 3. I'm going to say that one out. So that's 4, 5, 6, 7, 8, 9, 10. Let's call it 10. I don't know if I counted those right, but that's okay. So in the same distance, the same unit length, we're seeing something like 10 stationary phase interactions. Right, so we're getting a much, this is kind of the best way I can think of to visualize resistance to mass transfer, right? This thing has a lower resistance to mass transfer because it diffuses into that stationary phase really effectively. Okay, so how could we fix this? Because believe me, people have tried to fix this for LC, and it turns out to be, fixing this for LC turns out to be a core component of what makes GC better. So here's what it is, right? So if you want to increase, so to increase stationary phase interactions, well, what would you do? You would just make this thing a lot longer, right? You just have to increase the length of the column. The thing we have to remember, though, is that increasing the length of the column also increases proportionally the delta P, the pressure needed, just to remind you, the pressure needed to flow through that column. In fact, the way that we express this is with the Hagen-Poiseuille equation, delta P equals 8 mu LQ over pi r to the forth. So there's the radius of our tube, there's the length of our tube, there's the viscosity of the medium that we're flowing through the tube, there's the volumetric flow rate we're trying to achieve, and to achieve that volumetric flow rate under these conditions, we need that much pressure. So that shows us that we're going to need, if we dramatically increase, 10-fold increase the length of the column to get all those extra interactions with in the LC concept, we need to 10-fold increase the pressure. But actually, the Hagen-Poiseuille equation shows us another really, really, really useful thing about doing this in GC, this open tubular thing in GC, because gases have you know what? I feel so strongly about this. I'm putting a third arrow. They have much, much, much lower viscosity as compared to liquids. Right? Gases have extremely low viscosity, and that means we can get to these super long lengths without a huge price tag on pressure, because we have this other factor that is much lower for gases than it is for liquids. So commercial GC columns, these come in lengths up to 100 meters. That's a GC, that's a chromatography column as long as a football field. Well, as long as a football field if you follow the CFL. If you follow the NFL, that's a little longer than a football field. So whatever football you're into, I'm with you. Okay, the beauty of these super, super long columns is, of course, we know the relationship between H, L, and N, right? It's the height, gosh, let's see if I can remember this. So your number of theoretical plates is, your number of theoretical plates is equal to the length of your column divided by the height of that theoretical plate. So presuming all the chromatography is the same, the longer you get this column, the higher you get this number of theoretical plates. And I'll tell you that achievable theoretical plates in GC can be up to 500,000. Right? We're talking about 1 to 2 orders of magnitude greater than what we see in typical GC separations. Typical LC separations. So huge benefits here by going to really long columns, and you can do it because gases have this lower viscosity and therefore a lower price tag in terms of pressure to get up to these long column lengths. So I want to finish our little intro discussion on GC with sort of 3 take-home messages, right? So here's number 1. GC is uniquely suited for open tubular columns. And that comes with a lot of the benefits we've already talked about. So that's the second point, is that open tubular columns have significant benefits. We're talking about reduced A terms, which increases our number of theoretical plates. And we were also talking about longer columns, which also increases our number of theoretical plates. And this is how we get to really, really high values of theoretical plates in GC. This is why if you've ever done GC and LC, you've seen much narrower, sharper peaks in your GC than you ever see in LC. And then here's the last one, and this is going to kind of frame a lot of what we talk about. If GC works for your specific analyte, you're going to get increased analytical performance. You're going to get those better resolutions. You're going to get those higher plate counts. But you can only think about analytical performance here, and that's because GC is not a preparative technique, right? You're not gathering stuff at the end of the GC column, you're throwing it out at the end of the GC column. You're letting it evaporate off into space. Um, so if you need this prep, there's good news, and that is that few, if any, I actually don't know of any applications, few if any, um, work by GC. And by application, I mean analyte. Few, if any, analytes are going to be appropriate for GC, um, but not by LC. So if it'll work by GC, it will work by LC. If you need a preparative technique, you're going to have to switch over to LC because GC is just not well suited for it. All right, folks. Once again, longer than I expected it to be, but that's sort of the name of the game. Hope everyone's staying safe out there. I'm going to post the exam before the end of the day today. That is in the note that I'm posting these videos with on Canvas. So hopefully you've already read that. We're gonna get it before the end of the day today. I'm gonna give you a full week to work on it. So I am not feeling like timing of posting this thing is super critical. I'm gonna get it up before midnight tonight. Um, so yeah, I hope you guys have a great weekend. I hope you guys are all staying safe and staying healthy. And hey, do this for me. Get outside. We actually have some rare, or have had some rare, nice sunny weather in Knoxville. So just because you're staying away from people doesn't mean you have to lock yourself in your house, right? So get yourselves outside, enjoy life, and I'll see you next week.